balik. Hey, it's inner space people. Ever heard of the term electric potential? What about work potential energy? Does electric field ring a bell? These may sound like advanced concepts in physics, but it's actually quite simple once you get the basics down. Nonetheless, we are here to help you, as today we'll be talking about electric potential, work potential energy, and electric field, and giving you real-life examples of these topics. So first, let us define what an electric field is, and how exactly this is useful to us humans. How can we predict the reaction of an electrically charged object once it passes nearby another electrically charged object? Luckily, British scientist Michael Faraday came up with a way to do just that. He hypothesized that every charged object generates an electric field that permeates space and exerts a force on all charged particles it encounters. And he was totally right! An electric field is a measurable effect generated by any charged object. A field carries energy and passes it on to other charged materials by exerting electric forces. That would lead us to know these things. First, we need to know what is an electric charge. The easiest demonstration of this in real life involves rubbing a balloon on your hair and seeing how the balloon will then attract your hair when it sticks on the surface of the balloon. However, if two balloons have been rubbed on your hair, it will push each other away. These things occur because of electric charge, which is displaced due to the rubbing together of these materials. The hair becomes positively charged and the balloons become negatively charged. Opposite charges attract one another, which is why your hair sticks to the balloon, and like charges repel, which is why the two balloons push each other away. This property of electric charge is carried by certain subatomic particles. The most common of these are protons, which are positively charged, and electrons, which are negatively charged. As it happens, electrons, which are the essence of electricity, become easily transferable. And it is this transfer of electrons, in this case from your hair to the balloon, which generates electric charge from previously neutral materials. Each electron carries with it the fundamental charge, which is 1.6 times 10 raised to the negative 19 coulombs. This magnitude is negative for the electron and positive for the proton. By this, we can categorize substances by their ability to transfer electric charge, the conductors and insulators. As we all know, opposite charges attract one another because of electric force, also known as electrostatic force. This is outlined in Coulomb's law, which states that the magnitude of the electric force between two objects is equal to the Coulomb's constant times the charge on one object, Q1, times the charge of the other, Q2, then divided by the square of the distance between them. To put these things in an equation, the electric field E, created by a charged object, is the electric force F between the test charges divided by the magnitude of the test charge Q. So to find F, or the electrostatic force, we just have to use Coulomb's law. So to simplify this concept, we will use a diagram to represent it with vectors. So let us start with a positive point charge, Q1 and Q2. As we can see, Q1 is larger and stronger than Q2. So to plot the series of vectors between these charges, we will be using electric field lines. These lines are vectors that shows the magnitude and direction of the force exerted on any nearby positive test charge. The density of these field lines signifies the magnitude of the electric force on Q2, and when Q2 gets closer to Q1, the greater the force. And the logic also applies similarly to how we represent negative charges, although there is a slight difference. The electric field line diagram for a negatively charged point would look like the positive, but the arrow is pointing inward, meaning positive point charges would be attracted to it. Now let's combine two different charges. Let us say we have one positively charged particle and one negatively charged particle, with some distance between them, with an equal and opposite magnitude of charge. As mentioned earlier, opposite charged particles attract to each other, so we can add the fields together to create a total electric field. Let us examine the electric field because this will lead us to four important properties of electric field lines. First, the field lines must be tangent to the direction of the field at any given point. This means that if we place a positive charge anywhere, the field lines will point in the direction of the force exerted on positive test charge. This also means that a negative test charge would feel a force in the exact opposite direction. Next, the greater the line density, the greater the magnitude of the field. As a test charge moves closer to one of the fixed charges, the forces on it will be larger, thus the greater the number of the lines in that area. All of this means the lines is proportional to the magnitude of its charge. And for the third property is that the lines always start on positively charged objects and end on negatively charged objects. But if there is no negatively charged objects nearby, then the lines will just keep going infinitely, searching for a negatively charged object. Lastly is the fourth property, which states that the lines must never cross. These don't literally exist, but they are a convenient way to analyze the direction of a field at any point in space. So to make these things useful to us, we must step into electric potential. What is electric potential? Is it the potential of electricity? We all know that just as there is a gravitational potential energy by virtue of an object's position in a gravitational field, there is also an electric potential field by virtue of an object's position in an electrical field, and charged particles can flow and generate current, just like water in a river can. Why is this so? It is because of the field that does the work to produce acceleration. As charged particles move within an electric field, their electric potential energy changes. For a uniform field, the magnitude of this change is equal to the opposite of the object's charge times the electric field strength times its displacement from the reference point in the direction of the field, which leads us to the concept of potential difference, which is the difference in electric potential between 2 points in a field, expressed as the change in electric potential energy over electrical charge. The SI unit for the potential difference is the volts V, which is equivalent to 1 joule per coulomb, J over C. This means that as 1 coulomb charge moves through a potential difference of 1 volt, it gains 1 joule of energy. The potential difference for the two terminals of a common battery that most of you have in your houses is anywhere from about 1.5 volts for small batteries and around 12 volts to car batteries. The purpose of batteries is that they move charges, so we can say that volts are not a measure of energy. Hence, they measure change in energy per unit charge. As charge flows, it produces usable energy, like how water can push a water wheel as it moves past. This is the concept of electric current. But unfortunately, that would be for our next episode of Inner Space People. Hope you guys learned something and enjoyed this video. This has been Inner Space People. See you soon!